I think we are almost ready for the integration theory, and I hinted at it in the previous lecture. Okay. The measurability of a function turns out to be the primitive notion, fundamental notion, background notion for integrability. We already discussed measurability of a function. So with those things in hand, let us try to develop integration theory. So what we have is the following. You have R, the real number system. On the real number system, you have a sigma algebra M, the collection of all Lebesgue measurable sets, and you have a measure, namely restriction of Lebesgue outer measure to collection of Lebesgue measurable sets, precisely the Lebesgue measure. So this is the triplet that you should have in your mind when we start integration. R is the set, M is sigma algebra of subsets of R, and M is a measure on script M, which is the Lebesgue measure. And you have the notion of measurable functions. F from E subset of R to R, measurable, or even R extended measurable. So these two things you should keep in mind as a background material needed to start the integration theory. Now, as I hinted in the previous lecture, it is always good to compare and contrast with what is known to you, namely Riemann integration theory. And the basic ingredients of Riemann integration theory is as follows. You will integrate over a bounded interval. The integrand is assumed to be bounded. And if you want to integrate f over AB, what we do is you approximate f by step functions. So the picture will be something like this. You have an interval AB which is finite. You have a bounded function. You will approximate this function with the help of a step function by dividing the interval into several subintervals. And in each subinterval, you will assume that the function is a constant. Roughly, this is what you do. Okay. In other words, if you want to find density, mass of a wire of varying density, you will assume that the wire is simple, in the sense wire is obtained by grouping together several straight lines. Okay. What in Lebesgue integration that we are going to discuss in detail, the basic ingredients are as follows. This is what I mentioned at the end of the last lecture. Instead of intervals, bounded intervals, we will have measurable subsets of R. Measurable subsets. In fact, you may even, to start with, you may even assume that bounded measurable subsets. Bounded subsets which are measurable. Okay. And in place of bounded function, you will have measurable functions. And to start with, you may assume that the functions are bounded. Bounded measurable functions. And instead of approximating the given function by step function, we shall approximate the given measurable function by simple functions. Approximation by simple functions. So the right place to start is what is a simple function. Okay. I have intuitively told in the last lecture. Today we will start with the precise definition and properties of simple function. Now, to get an intuitive idea of simple function, go back to step function. To get step function, what you are doing is the total interval you are dividing into finite number of subintervals, and your step function is such that in each of these subinterval the function is a constant. Okay, we will do the same thing, we will mimic the same thing. The whole set we shall divide into several subsets. E1, E2, E3 and so on, such that, and the function is said to be simple if the function assumes constant on each of these measurable subsets. Okay, so exactly we mimic what happens in step function. So having said that, now let me give the precise definition. So far so good.
Yes, sir.
Is it okay?
Yes,
So
sir.
can we start with the precise definition? The
Yes.
definition runs as follows. A real valued function, for the time being, I will assume the function to be real valued. Extended, I will not take now. Phi. And also, I will assume the domain to be R. A real valued function phi from R to R is called simple if one. I will assume that the function is measurable because anyway, the measurability is going to be the crucial property that we need for the integration in later stage. So I will assume that whenever I talk about simple function, I will be talking only about the measurable function. If one, it is measurable. If you see some textbook, this condition they may not impose. Okay. So whenever they say wherever I say simple function, they will make simple measurable functions. Okay. So I will include measurability as an inherent part of simpleness. So to call a function to be simple, first of all, it is measurable. Then two, this domain, now the domain is R, you can decompose into several subsets. There exists E1, E2, and so on, En. Disjoint measurable sets. Such that their union, if you take, you get the whole domain. In our case, R. Union Ej is equal to R. J is equal to 1 to N. And third one, that phi should be constant on each of this part. There exists alpha I in R such that phi of x is equal to alpha I for every x in Ei. 1 less than or equal to I less than or equal to n. So this is the definition. You can see that this is exact counterpart of intervals and step functions. Okay? You are replacing intervals by measurable sets. That's it. Okay? Now, if you consider the measurable sets to be intervals, the same definition will boil down to step function. Next, we want to explore more about simple function, starting from a nice way to write simple function. Okay, that's first thing what we want to do. So for that, I would recall what is known as characteristic function. Recall. Let E be a subset of R, then the indicator function or a characteristic function chi E, chi suffix E, defined from R to R, chi E from R to R is defined as follows. As you all know, chi E acting on X will be equal to 1 if X is in E. Whenever you hit E, the function will switch on. And whenever you are outside E, the function will be switch off. 0 when X is not in E. Okay, so this is the definition of characteristic function. Now let me give you a few simple exercise based on characteristic function. They all will follow from the definition. Okay, 1. Chi of A union B, characteristic function of union on union of two sets is equal to characteristic function on first set plus characteristic function of second set, provided these two sets are disjoint. For disjoint sets A and B. Another property that we may need, you can establish this as an exercise. It's not difficult, just the definition. Characteristic function on intersection A intersection B will be equal to product of the characteristic function. Okay. And characteristic function on the union when A and B are not disjoint is characteristic function on A plus characteristic function on B minus characteristic function of the product. chi A into chi B for any A and B. Of course, the first one is a subcase of the second. Okay. Now, with this in hand, I would like to get a nice form in which we can express a simple function. Notation for simple function. So once you have a simple function, we are sure that it takes only finite number of distinct values, finite number of values. Okay. If alpha 1, alpha 2, etc., alpha n are distinct values taken by the measurable function of a simple measurable function. I don't have to say measurable, simple function. Simple function phi from R to R. Then I can write phi using characteristic function. Then phi can be represented as please keep in mind the property of phi. Phi is alpha I only on EI. Okay, and even E2, E3, etc., En are all disjoint. Therefore, you can write phi of x as follows. As phi of x is equal to, or I would write phi equal to, the given function phi is equal to, simple function phi is summation alpha I chi En. I is equal to 1 to n. Okay. Now what is EI? Where EI is equal to collection of all x in R such that phi of x is equal to alpha I. I is equal to 1, 2, 3, etc. up to that. It is not hard to see that phi can be represented like this. You just evaluate phi of x, see what happens. Phi of x is equal to summation alpha I chi ei of x. But chi ei of x will become 1 only when x is in ei, and it will be 0 in the rest place. Okay. Therefore, phi of x will coincide with alpha I whenever x is in ei. Do you agree?
Yes, sir.
Is that okay?
Yes, sir.
Yeah. And this representation is called canonical representation of a simple function. Okay. This representation of phi is called canonical representation. There may be many other representation for the same simple function. Canonical representation. You try. You take a simple function and try to write in different ways. Canonical representation. Let me make a few remarks here. So if you see while writing the canonical representation of a simple measurable function or a simple function, what I started with is only the distinct values taken by the simple function. The EIs naturally emerged. EI is a collection of all x such that phi of x equal to alpha. So what I concentrated on is what are the distinct values of the function taken by the simple function. Okay. So keep that in mind. Now, if the remark is very simple, but it is worth to record. If phi is summation alpha I chi I is equal to 1 to n, is the canonical representation. We are writing a simple function as a linear combination of characteristic function. Canonical representation of the simple function phi. This EI has a property. Simple function. EI, I already told. EI is collection of all x in R such that phi of x is equal to alpha I. That EIs will give then E1, E2, etc. En gives a decomposition of R. Gives a decomposition of R. What does it mean? That is, R can be expressed as union EI, I is equal to 1 to n, and E1, E2, E3, etc. En is a disjoint family. It's not hard to see. So the canonical representation automatically gives you decomposition of the domain into several pieces where each piece is a measurable set. Okay. Now, another remark that I would like to make here, again, it is a simple consequence of the canonical representation. Suppose the distinct values taken by phi are, say alpha 1, alpha 2, etc., alpha n, but I just ignore the zero value. Phi may be equal to 0 at some point. Okay, I ignore it. If phi takes the value 0, then the term, that alpha, the term corresponding to this value. Suppose one of these alpha I is 0, then I can ignore it. Corresponding to this value need not be written. In the canonical representation of phi. Do you agree? Suppose one of the alpha is 0, I can avoid it and write phi of x as summation alpha I chi ei for non-zero values of alpha I. Do you agree?
Yes, sir.
Yes.
However, you should be careful. Thus, one may assume alpha 1, alpha 2, etc., alpha n are non-zero values. Non-zero values of phi. If there is a zero value, you can ignore and then write it as summation alpha I. Okay. However, what's the thing that you should take care is the following. However, in that case, when you go for the decomposition of R, you should be careful. However, in that case, R will be equal to union EI, I is equal to 1 to n. That will not be correct. Union E naught. Okay. Where E naught is collection of all x in R such that phi of x is equal to 0. So without loss of generality, in the canonical form of a simple function, you can assume that the values taken by the simple functions are non-zero and you can consider only the non-zero values of alpha I to write this. But after writing, if you want to get a corresponding partition of the domain, you should be careful. Okay, just you take value ei to be collection of all x such that phi of x is equal to alpha I. That will not give you the partition of R. Okay? It should include with E naught. Another remark that in the line is the following. A function is simple if and only if phi is simple if and only if it is measurable. By definition, it is measurable and assumes only a finite number of values. One part is clear. By very definition of simple function, it is measurable and it has only finite number of values, alpha 1, alpha 2, etc., alpha n. Some of the alpha i's can be 0. Now, conversely, suppose it is measurable and it assumes only finite number of value. Do you see that phi is simple? Suppose a function is measurable and it assumes the range set is finite, alpha 1, alpha 2, etc., alpha m. Then do you see that that function is simple? Go for the definition of simple. What is definition of simple says? It should be measurable. That is already an hypothesis. There should exist E1, E2, E3, etc., En. Can you find E1, E2, E3, etc., En with this assumption? Take Ei to be what?
Inverse images.
Collection of all x such that phi of x is equal to alpha I. You take that, you will get Ei's. And since phi is measurable, collection of all x such that phi of x is equal to alpha I is measurable. You have seen it. Okay. So Ei's are measurable and Ei's will give you the partition of R and so on. Therefore, some authors, why I made it as a remark is some author defines simple function like this. A function is said to be simple if it is measurable and assumes only finite number of value. Some authors may not even worry about measurability. They would just say that a function is simple if it assumes only finite number of values. And whenever we say simple function, they will say simple measurable function in the theorems. Okay. To avoid that, I have included measurability in the definition itself. Okay. So third remark is straightforward, but why I included is this could be the definition in some of the books that you may consult. Okay. Anyway, so I hope simple functions is clear. Basically, it is a measurable function and the range set is finite. Alpha 1, alpha 2, etc., alpha n. Some alpha is maybe 0. If alpha is a 0, while writing it in the canonical form, you may ignore this 0 alpha is. Okay. Is that okay?
Yes.
So this is going to be the, I am going very slow here because this is the foundation for the entire course that we are going to give in the future days, forthcoming days. So simple functions are the basic. So once you understood simple function, what next we are going to do is to define Lebesgue integral for the simple function. Okay. And once you understand that, everything else follows. Now, how do you integrate a simple function? What Lebesgue did is just to mimic what Riemann did. How does in Riemann integration theory one integrate step functions? How do you integrate functions of this form? Suppose this is your interval AB and function takes value C1 on some interval, C2 on some interval, C3 on some subinterval, C4 and C5. How will you integrate this? Suppose this is your f. What is integral of f on AB? Yes.
Summation of Ci into interval Ei, length of interval Ei.
Length of interval Ei, right? So you are in exactly analogous situation. Instead of step function, you have simple functions. So instead of interval, you have R or maybe a subset of R that we will deal later. And this R is decomposed into finite number of measurable sets, E1, E2, E3, etc., Ek. And on Ei, the function has a constant value. Okay, so please recall that integral A to B f dx in Riemann sense is summation Ci length of Ii. I is equal to 1 to 5 for the given picture. Okay, so what we will do for simple function is the following. Can you guess?
Sir, summation of alpha I into measure of Ei.
Measure of Ei, that's it. Value that each function takes, values that the simple function takes, multiplied with quantification on the set on which that value is taken. Alpha I is taken on Ei. But now you cannot talk about length of Ei. You have to talk about some quantification of Ei. And the quantification of Ei is measure of Ei. Okay. So if you have that intuition in mind, now we can define what is integral of a simple function. Okay. Let phi be a non-negative. I would say why we are assuming non-negative. Simple function. Non-negative simple function. By definition, simple functions are measurable. Non-negative simple function with the canonical form. So once it is simple function, you can write it in canonical form with the canonical representation. Phi is equal to summation alpha I chi Ei. I is equal to 1 to n. Okay. And please bear in mind that when we write canonical representation, if phi takes at some point, I mean 0 values, you can avoid it if you want. Then the integral of phi, over R. Later we will avoid over R and we may talk about over any subset that we will see later. Now it is over R with respect to Lebesgue measure. With respect to the Lebesgue measure, M is defined as integral. I am going to define summation I is equal to 1 to n values taken by the function, that is alpha I, times where the value is taken is on Ei, but Ei is not now intervals. So I will multiply this with the quantification of that set, namely measure of Ei. And this will be denoted by integral over R phi dm. Integration is with respect to the Lebesgue measure. Okay. So this finishes integration for simple function. Okay. And you can see that again, this is exact counterpart of what Riemann did for step functions. But now it is more generalized. You don't have to be having subintervals. You can have any sets. Okay. So let me now just write some more notation generally people use for Lebesgue integral. Okay. Sometimes they use this integral over R phi dm. Sometimes they use this integral over R phi of x dm of x, just to differentiate it from Riemann integral. And if you are clear from the context whether you are working with Riemann or with Lebesgue, you can even use this, no issue. But now the integration is with respect to Lebesgue, and maybe this, just avoid dx, dm, etc., and just write integral phi, or maybe this also integral phi of x dx, just like Riemann. So all these things are interchangeably used in literature. Okay, so I will try to stick to the first one, integral over R phi dm. Integration is with respect to Lebesgue measure. Okay. Yeah. Now let me say a few words about this definition. First thing, why do you want non-negative? Can you guess why did you ask for non-negative?
Because the area is positive. If we take negative, then it will minus.
No, I am not talking about area or anything here. Why do you want a geometrical interpretation? I have defined something. I have defined integral of a simple function. That's it. Why do you want to correlate it with the area? That is nothing connected with area. It's a definition. My question is, in this definition, why do you feel this assumption of non-negativity is important? Look at the expression. I have defined integral over R phi dm to be summation I is equal to 1 to n alpha I m of ei. And you know that m of ei could be infinity. Measure of a subset of R can be infinity. Do you agree?
Yes, sir.
So suppose 1 alpha I you have positive, and 1 alpha j you have negative, which is equal to minus alpha I. You have an alpha I and you have a minus alpha I. Okay. And suppose measure of the EI is infinity and measure of EJ is minus infinity. Then you will have expression like infinity minus infinity, which will not make the right hand side meaningful. That's why we are assuming. Okay. Anyway, let me write it. Remark. In the definition, we shall assume that phi is non-negative. For otherwise, the summation alpha I m of ei may not be well defined. I will give you one instance when this well definedness can create issue. Since it may happen that for some I not equal to j, measure of ei is equal to measure of ej is equal to infinity, and corresponding values of the function alpha I is same as minus alpha j, and both are non-zero. So something like phi assumes the value 2 and minus 2, where it assumes value 2 is of infinite measure, where it assume value minus 2 is also of infinite measure. Then it will create issue. So that we may end up with expression of the form infinity minus infinity. And in the extended real number system, I told you that we will leave this undefined. We will not try to define this. Okay. Now, second remark. If alpha I is greater than 0 and measure of EI is equal to infinity in the canonical form for some I belong to 1, 2, 3, etc. up to n. Then for the non-negative measurable function, non-negative measurable function. Yeah, I want you to tell me what will be the integral in this case. Function integral of phi dm would be. Can you tell me? Phi is measurable. It is non-negative. Since it is measurable simple function, not measurability is important. Sorry. Simpleness. Simpleness, I already included measurability. Simple function. Suppose you have a simple function phi, which is non-negative, and you know that it has a non-zero value alpha I, and that alpha I, where it assumed, is of infinite measure. Then what will be integral of phi?
Infinity.
It will be infinity. I don't bother what is the other value. You will have one term, alpha I times measure of EI term in the summation. Okay, it will be infinity. If you want an example, okay, you take phi to be characteristic function on 0 infinity. Is this a non-negative function?
Yes, sir.
Is it a simple function?
Yes, sir.
It take only two values, finite number of values only, 1 and 0. Okay, so I can integrate this, right? What will be integral over R phi dm? The values taken times measure of the set on which that value is taken. Value taken is 1 on 0 infinity, and measure of 0 infinity is infinity. So this will be actually measure of 0 infinity. Are you with me? And that will be equal to infinity. Okay. So you can have a simple function whose integral is infinity. Okay. Now, this example and this remark should motivate the next definition. Let phi be a non-negative simple function. Non-negative simple measurable function. Sometime I would write simple measurable, sometime I will write simple, but keep in mind that, but for us, simple automatically means measurable. Simple function on R. Then phi is said to be integrable. Phi is said to be integrable on R if integral over phi dm, integral over R phi dm is finite. It can be infinity, value can be infinity for some function. We call those functions whose integral is finite to be integrable. Now we are only in the domain of simple function. Our collection is restricted to simple function. Okay. Now, so far we were integrating simple function, to be precise, non-negative simple function only over entire R. Now, suppose you are interested to integrate over some subset of R. Okay, so we are leading to that. We are heading towards that. Okay. So let us make an observation first. And remember, while defining integration or integral of a simple non-negative function, we seek help of canonical representation. Starting from canonical representation, we wrote what is the integral. Keep that also in mind. Okay. Now, but same simple function may be expressed in a different way. We are defining integral only via canonical representation. If phi is equal to summation alpha I chi ei, I is equal to 1 to n, is the canonical representation of a non-negative simple function. Function phi. Okay. Then you know how to define integral over R. Integral over R phi dm would be summation alpha I measure of ei. Now, what we do is the following. Then, for any E subset of R, any E subset of R, E measurable, E is measurable, Lebesgue measurable. What will be chi E times phi? I would like to know what is chi E function multiplied with phi function. Multiplication is pointwise. Fg of x is f of x into g of x. Okay. That will be equal to, can you tell me what it will be? Of course, this will be chi E times summation I is equal to 1 to n alpha I chi En. Can you guess what this will be?
Summation of alpha I chi ei intersection E.
Yes, I have already told the properties. You can apply that or you can apply the definition. Summation alpha I chi E intersection Ei. Okay. And this will be the canonical representation of the new function chi E times phi. Okay. Is the canonical representation. Those who are not able to get now, please take your time and try to understand why chi E phi times is this. Okay. Either you can use the properties of characteristic function I have listed, or you can apply the definition and see this equality. And further, you should convince that it is the canonical representation of chi E times phi. Okay. So once you have canonical representation for a simple non-negative function, you can integrate it so that integral of chi E phi dm integral over R will be equal to, yes, what will be the definition? Summation I is equal to 1 to n alpha I. Can you complete? Measure of E intersection Ei. Do you agree?
Yes, sir.
Once I have a canonical representation of a simple function, I can write its integral. Okay. Now, please keep in mind that chi E times phi is non-zero only on E. Agree? Look
Yes.
at the left-hand side. Look at the left-hand side. It is integral over R. The integrand is chi E times phi. But chi E times phi is non-zero only on E. Therefore, there is no harm to interpret the left-hand side integral as integral over E phi dm. What happens to phi on E and what happens to chi E phi on R are same. Yes or no?
Yes, sir.
These are all looking simple, but next important point I am going to make. This observation, so I have made an observation here. Once I have a simple non-negative function, I can multiply with characteristic function. I will get again a simple non-negative function. I can integrate it. So what? So the catch is the following. This observation motivates the following definition. Motivates the following definition. I don't know whether it motivates you for this definition, but I have already told the idea. Left hand side of the integral that I have written, if you see, it actually makes sense only on E. Okay, so if phi is a non-negative, simple, measurable, I don't have to write measurable, simple function on R, and E be a subset of R, which is measurable, then we define integral over E phi dm. So far we were doing only integration over entire R. Now we are integrating over any subset of R, integral over E phi dm. Okay, how do I do that? You interpret this as integral over R chi E phi dm. And how to do integral over R chi E phi dm? You already told. Once phi is simple, chi E phi will be simple. It has a canonical form, and you know how to integrate this. Okay, and it is called the integral of phi. The integral of phi over E with respect to Lebesgue measure. Yeah. So what the great thing that we achieve is that instead of integration over entire R, now you can talk about integration over any subset of R, measurable subset of R. Okay. Why measurability is needed? Finally, you want measure of E intersection EI. EIs are measurable, I know. But if E is not measurable, I cannot assure that E intersection EI is measurable. Okay, that's why I am integrating only over measurable sets. Okay, there is another way to look at it. Integration over a subset you can view in another way. Now, this is where I wrote in the beginning of this lecture. What is the basic ingredient we have is R and sigma algebra over R and measure on that. That's why we are integrating. So this is called measure space. Such a triplet is called measure space. A set, a sigma algebra, and a measure. This is measure space. Okay. So since your measure space is on R, you are integrating over R. But later, slowly you changed it into integration over E. But suppose you have a measure space on E itself. On the beginning itself, you have a measure space on E. That is E, some subset of R. Then M on that E and a measure on that E. Then you can integrate over E. Are you with me?
Yes, sir.
So in that way also you can proceed to get integration over E. So let me just make a remark. Alternatively, to define integration over E phi dm, we can proceed as follows. This is a bit complicated to proceed like this. That's why I went through chi E times phi. That's more easy. What I will want to do. If you want to integrate over E, you should know a measure space on E. But right now I know only measure space over R. R, M, M only I have. Okay. So, but from that I can construct a measure space on E. Proceed as follows. Okay. Let script M suffix E be sigma algebra restricted to E. And small me, M suffix E, be the Lebesgue measure restricted to script me. Restricted to script me. So now we have the measure space. Now we have E in place of R, you have E. And then you have a sigma algebra of subsets of E. And you have a measure. Okay. Now you can define, therefore, integral over E phi dm would be is equal to integral over E. Phi is defined from R to R. Now you restrict it to E. Phi restricted to E. And don't take the measure on R. This M, left hand side M stands for measure on R. Don't take measure on R, but you take measure on E. D M M suffix E. M suffix E. This is another way to look at integration over some measurable sets. Okay. So that means phi will have a canonical representation. Therefore, while integrating, you have to multiply it with summation alpha I. Suppose your phi is something like this. Summation alpha I chi ei. Okay. Now EIs are all inside E. Now, if you want to integrate E, it will be summation alpha I measure of EI. That's okay. But now the measure of EI is not in the original R, but it is with respect to this ME. That is why I wrote DM suffix E. Okay. After getting the canonical representation, you should integrate it like summation alpha I times measure of EI. But that measure should be in the measure space EME. It is not the original Lebesgue measure. It is the restricted measure on E. Are you with me?
Yes, sir.
So we don't have to worry too much about this remark. Our way of approach will be always we will have only a single measure space, namely R, M, and M. That is our measure space. If you want to integrate over sets other than R, what you will do is you will integrate over R the appropriate function. Instead of integrating phi, you will integrate chi E times phi, because the action of chi E phi is ultimately only on E. Okay. So let me give one example to illustrate this. Not this remark, but the definition. How to integrate over subset. Example. let E equal to AB, interval AB, which is inside R. Now I want to talk about integration of some function over E, not over R. Okay. Now let us consider A to be AB intersection Q, all rational numbers in that interval, and B to be AB intersection Q complement. Okay. Now I want to get integral over E, a simple function, which is the simple function I am taking, characteristic function on A dm. This is what I am interested. And similarly, I want integral over B, integral over E, chi B dm. Can you tell how to approach integration over E? We already told. To find integration over E, this will be same as integration over R. What I should do? Chi E times the function. The function is chi A. Chi A dm. Is that okay?
Yes, sir.
Now what is this? That is integration over R. What is chi E times chi A? I have given you a property. This is chi E intersection A dm. Right? But what is chi E intersection A? E is AB and A is AB intersection Q. So what is chi E intersection A?
Chi.
A.
So this is equal to integral over R chi E, right? Chi A, sorry, chi A. Chi A dm. Now, what about integral over R chi A dm? How do you find it? Chi A has only one value, that is 1, and only two value, 1 and 0. So you have to worry only about 1. And where it takes 1 is on A. So 1 times measure of A. Okay. So this will be 1 times measure of A. And what is measure of A?
0.
0. Because A is countable. Okay. So this is 0. And what is integral over E chi B dm, if I want to find chi B dm. If you want to integrate over E, either you should talk about a measure space on E by restriction and so on. That is one method. Or what you do is, don't worry about what is the measure space on E. You work on measure space of R itself. Okay. And then you integrate over R. But the function that I have to consider is chi E times the function. The function is chi B. That is again integral over R chi E intersection B and so on. You will get here it to be measure of what? B. This will be measure of B. And what is measure of B?
1.
Not
B
one.
minus A. Sorry, B.
minus A. B minus A. Yeah. And do you know that chi A and chi B are not Riemann integrable? What is chi A? Note that chi A is equal to, what is the definition of chi A? 1 if x is in A and 0 if x is not in A. Okay, that is 1 if x is in A means what? What is A? X is in AB intersection K. AB intersection Q, sorry, for rational number in Q, and 0 if let me write otherwise. So what is this? This is a famous Dirichlet function, right? 1 when x is rational and 0 when x is irrational. Is it Riemann integrable?
No.
But it is Lebesgue integrable with integral as
0.
0. That is what I told. This is what we expected, because see, chi A has 0 everywhere. except on a countable set, chi a is 0. So we should expect that the integral should be 0. That's what it happens when you integrate with respect to Lebesgue. But whereas with respect to Riemann, you cannot even talk about the integral. Okay. So this example I intentionally choose. One is to illustrate how to integrate over a subset, and other is to illustrate that Lebesgue has advantage over Riemann. Lebesgue has advantage over Riemann. Okay. So it is a simple but illustrative example. Okay. Now, so far what is our progress is, you started with step function. Then you made one more condition, non-negative step function, and you could integrate non-negative step function. How did you integrate non-negative step function? How did you integrate non-negative step function? Via what? Via its. It is really embarrassing when you don't respond. If it is not because you are not understanding the question, it is okay, but you have integrated simple non-negative function. Do you agree? At least integration of simple non-negative function we have already done. Do you agree?
Yes, sir.
Yes, sir.
How did you perform a simple non-negative function? How did you integrate? What was the starting point? You have to write it in what form? Canonical form. If you have a canonical form, look at the definition. This is the definition of integration. If you have the canonical form, I can immediately write the integration. Okay. So now what I am going to say is, suppose you have a simple function, let us say non-negative simple function, but it is not in canonical form. Then what? Then can we integrate? Can we do something? That's what we are going to do next. So I am very upset that you are not. This is the real point where our course started, and now you are not responding to any of my questions. Okay, so far we have done only background. This is the real point where our course started, integration theory. Okay, so what we did is we started with simple function. We made an extra hypothesis of non-negative, and for a non-negative simple function we have integrated, but integration is only when the non-negative simple function is written in canonical form. One thing. Secondly, we can integrate over R only. If you want to integrate over E, we made it in a slightly different way. That part also we have done. However, the issue still persists that we can integrate over R or integrate over E only when the simple non-negative function is in canonical form. What if it is not canonical form is the next lemma. Let P1, P2, and so on Bk be a disjoint family. Disjoint family of measurable sets. Of measurable sets. And please let me know if you feel that something is difficult. Beta 1, beta 2, etc. beta k be non-negative reals. Let psi I am writing as summation beta I chi bi, I from 1 to k. Before writing the lemma, do you see that chi will be simple? Do you see that chi will be a simple function? Yes or no?
Yes, sir.
What is simple means? It should be measurable and it takes only finite number of values. Only values are beta 1, beta 2, etc. beta k. So this will be simple. However, you cannot assure that this is the canonical form of psi. For canonical form, one more thing that you need is this beta 1, beta 2, etc., beta k. When you write summation alpha I chi ei, alpha I should be the distinct values taken by the function, and ei should be the point at which set at which those values are taken. We don't have any such assumption. Beta I need not be distinct. Okay, so this is not a canonical representation. However, then the lemma says that integral over R psi dm would be equal to summation k is equal to I equal to 1 to k, summation I equal to 1 to k beta I measure of bi. So what is the essence of this lemma? Let us not forget. Let us not worry about the proof now. What this lemma says, you don't feel anything new? Previously in definition also I have integrated a simple function. Now also I am integrating a simple function. What is new? The new thing is that the lemma says that you don't have to have the representation to be canonical. Any representation of simple function you take, you can have the integral, and the integral will coincide with the values taken times measure. Are you getting me?
Yes, sir.
So this lemma tells you that you don't have to have the canonical representation. Otherwise also you can. What's the difference between the given representation and canonical representation? In canonical, alpha 1, alpha 2, etc., alpha n need to be distinct. Here we didn't say that. Okay, proof. If beta 1, beta 2, etc., beta k are distinct, we are done, because in that case this will be the given representation. Then the given representation is its canonical representation. You should convince that canonical representation, and once you have canonical representation, and hence the proof follows. Proof means the integral to be equal to this follows from the definition. The proof follows from the definition. That is how we defined the integral of a simple function once it is in canonical form. Now suppose it is not canonical form. Next assume that beta 1, that is psi of x, is equal to summation beta I chi bi. That was the given expression. Is such that sum of, not SUM, sum of one or the other of beta 1, beta 2, etc., beta k are repeated. Maybe when I write the details, you can always think of something like this. You have beta 1, beta 2, beta 3, and so on, beta k. Possibly, this beta 1, beta 2, beta 3 may be same. Assume these are same. Okay. Beta 4 and beta 5 are same, and all others, beta 6 onwards, is distinct. Just as an example. Okay. Now what I do is, from this beta 1 to beta k, I will extract the distinct one. Suppose alpha 1, alpha 2, etc., alpha n are distinct numbers among beta 1, beta 2, etc., beta k. So in this example case, beta 1, beta 2, beta 3, everything everything may be alpha 1. Beta 4 and beta 5 is alpha 2. And beta 3 is alpha 3 and so on. Beta 6 is alpha 3 and so on. This is alpha 1, this is alpha 2, this is alpha 3 and so on. And like that alpha n. Okay, this example you can keep in mind while I complete the rest of the details. So n would be obviously less than k. Now for each I element of 1, 2, 3, etc. up to n, I define delta I to be, I am grouping set of all j such that beta j is equal to alpha I. For in this example, delta 1 would be 1, 2, 3. Beta 1, beta 2, beta 3 are same as alpha 1. So delta 1 would be 1, 2, 3. Delta 2 would be 4 and 5. Beta 4 and beta 5 are same, and that is alpha 2. Okay, so delta 2 would be 4 and 5. Delta 3 would be, and like that, so on. Others will be singleton sets. Okay. Now clearly, so what we did essentially is that from the given list, we extracted the distinct list by grouping. Now clearly, I will not give the details, you have to convince yourself. Psi is given to be summation j is equal to 1 to n beta j chi bj. That is given expression for psi. But you know that for in this example, for instance, beta 1, beta 2, beta 3 are all alpha 1. So 3 terms of this summation will have same coefficient alpha 1. And you will have chi b1, chi b2, chi b3. So this I can group as summation I is equal to 1 to n, summation j belong to delta I, beta j chi bj. Convince yourself with the example that I have given. Okay, and this is equal to summation I is equal to 1 to n. When j belongs to delta I, beta j's are same as alpha I, summation j belong to delta I chi bj. Okay, and that is equal to, now I am going to make use of the properties of characteristic function alpha I will write this as chi of ai. Summation j belong to delta I chi bj, I am writing as chi of ai. Can you guess what will be ai? Well, ai is equal to, I will be more than happy if you can say
Union of BZ.
Union bj. Okay, j belong to delta I. Note that measure of ai is equal to summation measure of bj. J belong to delta I. Remember B1, B2, B3, etc. BK are
Disjoint.
disjoint. Yeah. Is it given? Yeah, it is disjoint family of measurable set. Have I written that? Yes, disjoint family. Okay. So with that, measure of AI would be this. And further, the new sets that you have formed, A1, A2, etc., AN, is a disjoint family. Is a disjoint family. So what did you achieve? You achieved that this alpha I chi ei, this happens to be the canonical form. Alpha i's are distinct now. Therefore, integral over R psi dm is equal to, now since it is in canonical form, I can define the integration as summation I is equal to 1 to n alpha I measure of ai. Okay. That is summation I is equal to 1 to n alpha I. Measure of ai is summation j belong to delta I measure of bj. Okay. That is equal to summation I is equal to 1 to n summation j belong to delta I alpha I measure of bj. When j belong to delta I, alpha I is same as beta j. So summation I is equal to 1 to n beta I. Okay. Beta I measure of bi. Okay. And that's what it is asked to prove. Beta I measure of bi. Okay. So what essentially it tells you that it's all computation. So I don't want to spend more time on it. You sit down and try to understand it by taking an example like how beta is repeated, then how do you get distinct from it, how to form this delta I, and so on. Okay, so everything will follow with the notations delta I if you understood this notation delta I properly. But the essence of the theorem or the lemma is that I don't have to have the canonical representation. Without that also I can write. Now let me give you one example at this juncture. Again, it is a simple example, but it is very illustrative. Let phi be a step function. Let phi be a step function. In particular, it is a simple function. Phi is equal to summation alpha I chi I. I is equal to 1 to n with I am assuming alpha I to be greater than or equal to 0 because so far we discussed only about non-negative step functions, non-negative simple functions. Okay, then phi is a simple function, no doubt about it. Okay, now I will assume I1, I2, I3, In to be disjoint. Let I1, I2, etc. In be disjoint intervals. Disjoint intervals whose union is AB. Now I want to find integral over AB phi dm. Phi is a step function. It's a non-negative step function. So in particular, it is a non-negative simple function. And for a non-negative simple function, I know how to integrate. Okay. Now, one thing, I want integration over AB. I know only integration over R as such. So first thing you need to do, convert it into integration over R. Chi AB phi dm. Is that okay?
Yes, sir.
Now, phi, I don't have canonical representation. I have only one representation. I don't know whether it is canonical or not. However, the lemma says that I can integrate it, right? How do I integrate? This will be equal to summation. Yeah, can you tell me? Alpha I times
I intersection AB, measure of.
but anyway, it is inside AB. Everything is inside AB. I1, I2, I3, etc. Disjoint intervals in AB.
Length of II.
Length of II. Measure of II, intersection AB, which is same as measure of II, and measure of II is same as length of II. I is equal to 1 to n. I am not bothered about whether this phi is in canonical representation or not. I don't bother. By the using previous lemma, by previous lemma. So two things I have used here. One is the fact that I want integration over a subset. Doesn't matter. I can change into integration over R. Secondly, I am not bothered whether the given simple function is canonical or not. I can use the lemma to get the value. And what is this?
Riemann integration.
Riemann integration, because phi is like a step function. Alpha 1 on I1, alpha 2 on I2. I don't bother whether alpha 1, alpha 2 are distinct or not. I don't bother. I mean that canonical representation or not, I don't bother. But finally, the integral value will be summation alpha I, length of II. That means we are getting back the Riemann integral, which is Riemann integral. Whatever Riemann can do, I can also do. That's the Lebesgue. Whereas I can do something more which Riemann cannot do. Okay? So that philosophy I wanted to reassure through examples when and where possible. Okay. So I think this is the best place to stop. What next we do is, so now our progress is only this much, starting with a fundamental notion of simple function, we could integrate simple function. Okay. We could integrate simple function, that to non-negative simple function, whether over R or whether over E doesn't matter. Whether you have the simple function in a canonical form or simple function in some form doesn't matter. We can integrate it. Okay, that is our progress so far. Next, okay, you did integration for at least some class of function, non-negative simple function, you could integrate. First, we should convince ourselves that the integration we are done is well behaved. Like, you know, in Riemann integral, you have integration of sum of two function is sum of the integrals, right? And product and so on. So these type of property you have to first verify for simple non-negative function. So that's our next aim. Some theorems which will tell you that the integration you have defined so far is well behaved with respect to summation, with respect to multiplication with a constant and so on. That is one thing to do. When I say well behaved, I also mean that suppose you have f less than or equal to g, what do you expect? Integral of f should be
Less than equal to integration
so
of
those things, those property which we expect, whether it holds good for Lebesgue integration, which we did for a non-negative measurable simple function, that we have to verify first. So that is first. Once you verified this, step 0 is over. I will just give you an overview of what we are going to do. So that will finish step 0. That means you have integrated only non-negative what? Simple function. Non-negative simple function. Now first step, that is 0th step I would call. Now the next step is how to integrate other functions other than the simple functions. Okay. There, I will first use boundedness. I don't have time. And then I will again follow the Riemann idea. That is, underestimate and make the underestimate better and better, or overestimate and make the overestimate better and better. That is, you should recall here the upper Riemann sum, lower Riemann sum, upper Riemann integral, lower Riemann integral, and so on. Same idea we will mimic here. Underestimate and make it better, overestimate and make it better. But that I will do for the measurable non-negative functions. So that is step 1. In step 2, I will avoid this. In fact, I will also use boundedness. In step 2, I will avoid this boundedness and I will work with non-negative measurable function. That is step 2. And in step 3, we shall avoid any of these restrictions. We can have even non-negative we can avoid. Okay. So first for non-negative simple function. Next for non-negative bounded functions, and next for non-negativity can be avoided for any function. So finally, we will reach how to integrate any function. Of course, with the measurability as the basic condition. Okay. So I know I was a bit, not that clear at the end. That is okay. I am giving you an overview. So this is our step 0. We could achieve only integration of a non-negative simple functions. Okay. That as the starting point, we shall slowly go towards the integrability of any measurable function. Okay. That is, we cannot do at a stretch. Step by step we have to do. But every time we will be mimicking what Rayman has done. I think that is just an overview. But before that, we should see what are all the property that we expect for an integral is satisfied for integration we have done so far. That is for a simple non-negative function. Is that clear?
Yes, sir.
Yes.
So we will develop the properties of simple non-negative function, and we will stop the non-negative simple function business there, and that will end our 0th step, starting point. Then we will slowly extend it to general function step by step. Okay. It's a nice idea if you really appreciate. I mean, Lebesgue idea is really nice.